some X-rays ideas are involved, because again fast moving electrons, when they strike that the filament, no, tungsten filament, again they'll give out X-rays. That X-rays is electromagnetic waves. Will be very it's based on X-rays concept. Okay, now read the question. There's a very fundamental question. Based on this, I think some 5-6 numericals are there we can manage here. So there's a sphere, metal sphere. So its work function is 3 electron volt and the radius is 8 millimeter. The power of source is 3.2 millimeter, and there's a bulb, source of light. There's a source of light. There's a bulb you write, which will emit the photons of energy 5 electron volt, and the power is that much. So what is asking now? The efficiency of photoelectron emission is 1 for every 10 to the power of 6 incident photons. Assume that the sphere is isolated and initially neutral, and that the photoelectrons are instantly swept away after emission. No cloud formation will be there, but practically there will be a cloud. Can you remember? Space charge layer must be there, because you don't get all the electrons, photoelectrons will not be ejected with maximum kinetic energy. Some with zero kinetic energy, so there'll be a cloud. But he has made a situation instantly swept away. So that is another condition. So no space charge layer will be formed around this metal sphere. Calculate the number of photoelectrons emitted by this metal sphere. It is observed that photoelectron emission stops at a certain time t after the light source is switched on. Why? Question mark. Calculate that, evaluate that time t. Now, is it all the incident light falls on the metal sphere? No, only a fraction. So if you see this, the light which is within that cone what will happen will be incident on this metal sphere. No, the light emitted by the bulb, only one which is confined within this cone what happen will be incident on this one. So how to calculate number of photons incident? Again, the can you remember? I think very first day the photon flux like this we brought. First, number of photons emitted by the source. Number of photons emitted by source per second. So this, I think we use symbol, this one, Ns. There should be power of source by energy of photon. We'll retain the same symbol. So this will be 3.2 into 10 to the power of minus 3. Energy will be 5 into 1.6 into 10 to the power of minus 19. These many number of photons will be emitted by the source per second. Just to carry on the problem, you can feel like you can. So after getting this, after getting this one, is it all emitted photons will they strike metal sphere? No, only the fraction which is only the photons which are confined in this cone. So how to determine that one? For that, I'll go for photon flux. So what is the photon flux? It says photon flux should be equal to number of photons emitted by 4 pi. This symbol x, I'll make it 4 pi x square. So we know ns. Substituting that, we'll get the photon flux. Number of photons emitted per. So don't call, just call photon flux. So what is the idea of this? I'll assume a sphere of radius x. Then the photons will be emitted in all directions. Only a fraction of that, what happened, will be incident on this. So now I got photon flux. Photon flux into effective area. See, you look at the radius of this metal sphere, 8 millimeter. That of the distance, 0.8 millimeter. So shall we take condition? So for the bulb, how do this metal sphere will appear? Like a effective area will be like a surface, like a circular disc only. Though it's a spherical, it will appear like a circular disc only. The effective area we have to take. So number of photons incident on sphere per second. So this should be Ni is equal to everything will come per second here. Photon flux into effective area. Don't try 2 pi r square. Now by this time, in fluid mechanics you have come across the effective area should be pi r square here. So we got the incident photons. Now we have efficiency. For 10 to the power of 6 incident photons, incident 1 photoelectron. If Ni photons are incident per second, then how many photoelectrons? All these will be Ni photons incident per second. Then how many photoelectrons will be ejected per second? Any photoelectrons I think so. We know Ni. So that particular thing is there. So we'll get the Ni that one. So Ni is equal to Ni by 10 to the power of 6. So these many photoelectrons will be ejected. So as the metal now isolated, no, as it ejects photoelectrons, it will acquire a charge, So what will happen to the charge of this sphere? Will keep on increase. The charge of that sphere will keep on increase. Then it will acquire a charge, and then how to bring that one? So what is the charge on a sphere? Should be Ne into charge of electron. So after with the time, what happened to number of photoelectrons will continuously will leave the metal sphere. So the particular sphere, what happened will continuously it starts acquiring a charge. So then here I'll draw the diagram. Little bit big, I'll show it. So to explain concept. And this is the radius of the sphere r. So at any instant of time, let q be the charge. So what should be the charge? Q should be equal to E into Ne into T. Shall I write? Why? Because what is Ne? Ne is what? Number of photoelectrons ejected per second. So into time, that will give the charge. No? So what is this Ne into T? Will give number of electrons. So if you want to write that bracket, Ne is number of electrons ejected per second. In time t, how many electrons are ejected means Ne into time t. What is this? Total number of electrons left sphere in time t. And now what is the potential of this particular point P? Power already is there, no? So we'll take it A then. What is the potential of point A, no? So according to the electrostatics, potential of point A should be equal to KQ by R. K is what? 4 pi epsilon naught. So with the time, what will happen? The potential of that keeps on increases. Because of charge deposited here, because of charge acquired by this. And there's a light continuously incident. I'm not showing it. The electrons will be ejected, no? And there'll be an electrostatic field is set up, no? Because potential is non-zero. This electric field is due to what? Due to this metal sphere. Now, let's come for any ejected electron. So the ejected electron, this ejected electron, it will have kinetic energy K max. I'll take this color. Okay, and there's a point. Let's do one thing. The ejected electron, what happen, will have kinetic energy, no? Now tell me, like, this electron, what will happen to it? So when it is here, it will encounter kinetic energy will be K and electrostatic force. So all these electrostatic force will retard it. So initially, what will happen? The electrons will happen, they'll have sufficient kinetic energy, they will escape to infinity. They'll escape to infinity. Then as the electrons keep on escape to infinity, what will happen to charge on metal sphere will build up. As the charge on metal sphere increases, the electrostatic field increases. Then electrostatic force, retarding force on the electron, this is photoelectron. The electrostatic force on the photoelectron will increase, the retarding force will increase. So therefore now what will happen? At one instant, what happened? The kinetic energy, this kinetic energy of the ejected photoelectron will not be sufficient to escape to infinity. So before reaching infinity, the path traced by the electron, this electron, the path traced by this electron will be like this. Initially, electrons will escape. After some time, what happens? The electrons open will, the kinetic energy will not be sufficient to escape to infinity. Any reason for that? Because as the metal sphere continuously loses charge, the potential increase, the field strength will increase. Then the kinetic energy will not be sufficient to escape to infinity. So this would be path of. So altogether, how many photoelectrons ejected? All they will get back and will strike back the metal sphere. No? So altogether, shall I say that net photoelectron emission stops, but don't say photoelectric effect will stop. It is nothing similar to stopping potential. The idea of stopping potential here. So what is the path of electron? The electron, initially the electrons will escape to infinity. Then, so after one instant of time, the kinetic energy will happen will not be sufficient. Means as it moves, it will undergo retardation. Before reaching infinity only, it will return back and will strike it. So net photoelectron emission, we have to say 0, but there will be a photoelectric effect. He's asking that time. Calculate number of photoelectrons emitted. So he's asking to get all that particular thing and evaluate that time. When do that particular time will occur? So how to bring that one? So shall I apply conservation of mechanical energy from point A? Here, what all it's having interaction potential energy. The electron will have interaction potential with metal sphere and also kinetic energy. Just before reaching infinity, it will come to rest. So what is interaction potential? It will be 0. Kinetic energy should be 0. So applying conservation of mechanical energy. Initially, mass of electron. Oh, there's a K max, no? Okay, directly we have K max minus this will be K charge of this into E by R. Interaction potential energy. Shall I write? Or if you want, you can write potentiality. Charge of electron into potentiality. This should be equal to finally 0 plus 0. So K max we know how to get K max, SC by lambda, or energy of photon minus work function, minus of this is E K Q by R equal to 0. Do we know all the quantities we know? So what is Q? Q, I am going to substitute this. So if I continue further, EP minus phi E K E square NET by R equal to 0. Solving this, we'll get expression for T. And this will be 11.11 second. Check it. You'll get this much here. After this time, what happens? The net photoelectron emission stops here. Any good questions can be asked here. There's a one basic fundamental problem here. From where that electrostatic field will come? Due to the photoelectrons getting emitted from the metal sphere. That only will produce the field. it'll get charged here, no? Finally, what happened? What will be the charge on that? Will remain some fixed value, no? Here, I think there's an ideal thing where practically what will happen, there'll be a cloud will be formed and the electron goes, sometimes it'll collide, and we know collision of electrons will be elastic and they'll get deflected. So it's another thing, that one. Retracing path. I use word retracing path so that it will strike for you. It will move and returns back. I'll go for next one. This week portion, photoelectric effect, radiation pressure, matter waves.